So let's see, 10.5. So what we're going to do in order to come up with a way to find areas of various curves enclosed by curves and polar coordinates is we're going to use sectors of circles. So I'm going to say recall something else that we have been presented at one point. If we have a sector of a circle, so something like this. So a slice of pizza. And this angle is theta, and our radius is r. The area of a sector, A, is 1/2 r squared theta. And if because we're in radians, our arc length here is r theta. And we can kind of think of this as a little triangle. So 1/2 base times height. All right, so if we have a function, if r equals some function of theta, and we want the area we're interested in the area from theta equals alpha to theta equals beta. What we're going to do is we have some kind of region. Let me sketch a little graph here. And we're going to use this hopefully will become a familiar argument when we talk about these kinds of things. So we have some curve. And this is given by r of theta. And we want the area enclosed by this from theta equals alpha to beta. So this is theta equals alpha, and here we have theta equals beta. What we're going to do is divide this into small subintervals, so small little pieces here. And we're going to call this, the angle that's here, delta theta. And we're going to call the radius here r sub, and I'm going to call this theta sub I, r sub I. And then what we're going to do is add up the areas of these little sectors as we go from theta equals alpha to theta equals beta. So we subdivide our interval, and we're going to say our area is going to be approximately the sum I equals 1 to n, however many pieces we break it up into, 1/2 r of theta sub I squared delta theta sub I. And then we take the limit as n approaches infinity, as delta theta approaches 0. And then we get the definition of it's essentially a Riemann sum, so we get the definition of an integral. So take in the limit. Our area is going to be 1/2 the integral from alpha to beta of r squared d theta. And I'm going to put r of theta squared. Our radius is a function of theta, and we integrate. All right, so questions there. Well, let's look at an example, a quick example, and then we're going to talk about a couple of other interesting things that happen with polar area. Let me grab my picture though. Chapter 10. All right, so we're going to talk about we want to find the area of this nice cardioid, the same one we talked about yesterday. So we want to find the area enclosed by this cardioid. Now, one thing to be careful with when you're evaluating integrals, when you're finding areas enclosed by curves, is you want to make sure the interval on which they are traced one time, because it's possible, depending on the function, that the function may be traced multiple times between theta equals 0 and theta equals 2 pi. So if you're not sure, you should graph it in your calculator, make sure you're not being traced twice. Or we could say, in this case, r equals 0 when 2 plus 2 cosine theta equals 0, and if you look at that equation, set it equal to 0, you get that the radius is 0 at 0 and 2 pi. So this is traced once. Between 0 and 2 pi. And I'm just going to write as a note, see by solving 2 plus 2 cosine theta equals 0. So what I'm going to do here is the graph is symmetrical. So I'm just going to find the area enclosed by the top half and multiply by 2. So our area is going to be 2 integral from 0 to pi of 1/2. And I'm going to factor out the 2, and then we'll square it. So 1/2 times 4, 1 plus cosine theta squared d theta. So we end up with a 4 integral from 0 to pi, 1 plus 2 cosine theta plus cosine squared theta d theta. Well, these first two are pretty easy, right? What about that one? We have an identity. This type of quantity shows up frequently in polar coordinates. So we're going to say this is 4, the integral from 0 to pi of 1 plus 2 cosine theta. That sine squared theta and cosine squared theta show up often in these integrals, plus 1 plus cosine 2 theta over 2 d theta. This shows up frequently. And this is not too bad to evaluate. When I evaluate this, I get 4 times 3/2 theta, because I get a 1 theta here and a 1/2 theta here. 3/2 theta plus 2 sine theta plus sine 2 theta over 4, and we're evaluating that on 0 to pi. So that I took the 1/2 and the 1 here and put them together. For that one, be careful, again, be careful when you're evaluating definite integrals in polar coordinates, because trig functions have values when theta equals 0. So don't just say, oh, it equals 0, I can ignore it. This comes out to, when we evaluate it, comes out to 6 pi. So the area of that, area enclosed by that cardioid is 6 pi. This identity you will see often. You should at least be familiar with it. So you know, oh, there's that identity for cosine squared, or there's that identity for sine squared. All right, questions? Okay. Next, we're going to talk about the area between curves. So what we're interested in here is, I'm just going to make a little sketch. We have some function here, R2, and some function here, R1. And we want the area between these two curves from theta equals alpha to theta equals beta. So in kind of an everyday language, what's going to be our technique here? Top minus bottom, big minus small. So our area, big minus small, top minus bottom. That's how we think of these. So our area is going to be, in this case, 1/2. The integral from alpha to beta of R2 squared minus R1 squared d theta. So we're just subtracting to find that area in there. But I'm going to say be careful. Because sometimes finding the area enclosed by two polar curves is not as easy as top minus bottom. So let's look at an example of where that happens. Let's say we have, I'm going to do these in 2 different colors. So I'm going to start with a circle. There's my circle. I'll do the circle in red. So let's say we have a circle there. I'll put my coordinates, my axes on here. So there's my circle, and I'm going to hand draw a cardioid in blue. So my cardioid is going to look like not a bad cardioid. So we have a circle and a cardioid. And we want the area of their common interior. If we did just big minus small or top minus bottom, we would get the area in here. But that's not the area that we want. So what we're going to do, so just to what you want to visualize when you're finding areas of polar curves, I visualize the radius sweeping out the area. So from theta equals 0 up here to pi over 2, we're sweeping out just the area of the circle. But then we get to here, and we start sweeping out the area of the cardioid. So to find the area of the common interior, you have to add those two together. So it's not big minus small or top minus bottom. In the first part, it's just the area of the circle. And in the second part, it's just the area of the cardioid. And you would add those two together. That would also happen, for example, if you had a circle and a rose curve. So here's a petal of the rose curve. For this section, you would just be sweeping out the area of the rose curve until you get to the intersection. And then you'd sweep out the area of the circle. And then here you'd sweep out the area of the rose curve again. So to get the area of the common interior, you would have to split that up into 3 pieces. And that would depend on where they intersect here. And add those 3 areas together. So depending on the problem, it's not always as easy as big minus small or top minus bottom. The big minus small here would get us this area between the petal and the circle. So sometimes often you have to be careful. Sometimes it's not as easy as big minus small. I think you have a homework problem where they ask you to find the area inside a spiral. Something like that. And as we sweep out from 0 to pi, we sweep out that area. But then from pi to 3 pi, we're going to sweep this way. And we're going to sweep out that area again. So you have to subtract that middle piece, and depending on how many pieces of the spiral you want, you have to successively subtract areas that you've already found.
So why couldn't you just sweep from the end?
What's that?
So if you were to go and say, do 1, so how many times does that particular tog go around? 1 and 2, so that'd be a 2-ish.
Right.
So if that were to go to 2 pi, couldn't you just sweep 2 pi back, and that would give you the area, because then you won't have to subtract anything, because you don't find the area of the inside, you just find the area of the outermost perimeter. So if you were to, this one sweep from...
So if we swept this way, as we're going this way,
yeah,
you're going to sweep this area also.
Yes, but that's what you want to do. You want to sweep all of it. So you don't do any subtraction. So if you were to sweep from pi...
No, then if we sweep, then once we
if
get to here...
2 pi to 3 pi, what would happen?
No, then if we sweep from here, we're going to get that again.
No, but we'd stop right and try to...
But if we hadn't already done that, if we were to, on this spiral, if we were to sweep from 2 pi to 3 pi, what would happen?
From 2 pi to 3 pi? Let's see, so I think 2 pi gets us here. 2 pi to 3 pi would get us that piece.
But wouldn't that get us everything on the outermost, everything on the inside? If
2 pi.
there's...
No, 2 pi can give you that,
I'm not sure. It might. It might. But anyway, you can't just go from 0 to 3 pi or whatever on this one. You have to be more careful with it in some way. All right, questions there. Another thing to be careful with is finding intersections of polar curves. Sometimes solving simultaneous equations will not give you all of your intersections. And that is because polar coordinates are not unique. So let's look at an example where this happens. So we'll have two circles here. And here is one. And here is the other. That's a circle. This is r equals 2 sine theta. And this is r equals 2 cosine theta. And let's say we want to find this area here. So we need to know where they intersect. So we find the intersection by saying 2 sine theta equals 2 cosine theta. That's how we would normally find how two curves, or where two curves intersect. And to solve this, I would say divide by 2, and I would divide by cosine theta. I would get tangent theta equals 1. And that tells me that theta equals pi over 4. So here they intersect at theta equals pi over 4. Why didn't we get this?
Because that's at the pole and that's
R equals 2 cosine theta equals 0 at 0 pi over 2. R equals 2 sine theta equals 0 at 0 pi. They intersect at the pole at different values of theta. So how would we have to evaluate that integral? I think what I would do is just go from 0 to pi over 4 and multiply by 2, since it's a symmetrical region. So that would get you, we split it here and just find the area on that half, and then multiply that by 2. So often you need to graph to make sure you're getting all of your intersections.
Just figure out when r is equal to 0 for both times and when theta is equal to each other.
Does it always happen at the pole? I don't know. I'm not sure that it always happens at the pole. So
If it's not at the pole, how would we figure it out?
by graphing. So I would strongly recommend when you're doing these things to do a graph in your calculator to make sure you're getting all the piece of information that you need. All right, questions? Let me look at this. I have, if I remember correctly, I have a demonstration here with the idea of polar area sweep. And then maybe we can look at some nice polar graphs, since we have some time.
nice photograph.
Huh. Didn't like that one.
My brain is wired. If I have an equation, I have to go into the equation. I'll use the equation.
It takes a while for this to open up because I don't have the most powerful computer in the world. Yeah. No, this is Mathematica.
Oh, this is Mathematica.
Yeah.
Yeah, that's